Great. All right. So again, I try not to keep you too late tonight. Um, the Now I have been working on the test today. I've completed it, but I do, before I put it, make it online, ready to go, I do want to take it myself. That's what I usually do, take it myself to make sure there's no issues with it. So I'll be doing that after this meeting. That's why I don't want to keep you too late, because I don't want to stay up too late doing that. All right, but if everything seems fine, then it'll be available 6 a.m. tomorrow morning. Okay. And then you have until Friday at 11:59 to complete it. All right, will that give you guys enough time? Should be enough time. And Han, I did give you 90 minutes to complete the test.
Thank you.
Yeah, you have 90 minutes now, so there we go. All right, so let me just take a quick look, see if I can find, here we go.
I have a question.
Yeah.
Can we look at where we did incorrectly in the quiz? Because I only got the score and I didn't know where I did incorrectly.
Which quiz? You mean the quiz that I graded in the past?
Yeah, quiz 4.
Quiz 4.
And quiz 3 for the last question.
All right, I can do that at another time just with you, if you don't mind.
Okay.
Yeah, it would be better to do. So we'll set up a time where I can have a mini session with you, and we'll go over whatever questions.
Okay, thank you.
Yeah. Okay, good. And I'll complete all the rest of the grading over the weekend. That way you can combine all those quizzes that you have questions on into one, all right? So we can do that.
Okay, sounds good.
All right. Good. All right, so let's go to chapter 9. All right, now, chapter 8 is really a lead up to what we'll be covering for the rest of the course, starting with chapter 9. And chapter 9, if you look at the title for chapter 9, it says estimation from sample data. And so what we're going to do in chapter 9 is we're going to estimate a population parameter, either a mean, population mean, or a population proportion with sample data, right? And one type of estimation that we can use is what's called a point estimate, which is a single number that estimates the exact value of the population parameter. So if we were going to estimate the population mean, we would use a good point estimate. I mean, there's could be several, but a good point estimate would be the sample mean. Some people might think it's a sample for, median maybe, but the sample mean would be the best. And there's statistical reasons why it's considered the best. Besides the obvious reasons, right? Because it's the mean and sample mean, and we're estimating the population mean. The same thing with proportions. We're going to estimate the population proportion with the sample proportion, right? But the problem is that due to sampling variability, if Steve, if you do one sample, you'll get one result, and Han, you do another sample, you get a different result. Question is, which one is right one, if there is such a thing as a right one, and which one is the better of the two? Well, we really don't know, because we're estimating something that we don't know about. We don't know what the population mean is or the population proportion. Okay, we'll also be talking about, by the way, difference in means and difference in proportions if we had two samples for two different, what we would call subpopulations, all right? Some categorical variable that we are sorting population by, such as gender or age or something else. We want to look at the difference between the two population means and the difference between two population proportions. What are we going to use? Well, we'll use the same thing. The difference in the sample means and the difference in the sample proportions would be our point estimate. Same idea. But again, sampling variability would result in different samples producing different results for the sample results. So it became apparent to statisticians that we can't just use a point estimate. We have to use what's called an interval estimate. All right. And this whole idea of a sampling distribution plays a role in coming up with an interval estimate. An interval estimate would be a range of values that would estimate the population parameter instead of just one. And you derive this interval estimate from what? You derive it from the point estimate plus information about the sampling distribution. Those two things together, you create an interval estimate. Okay? So that's what we're going to learn how to do in this chapter, is to create this interval estimate. And the name of this interval estimate is a confidence interval. So that's what the next section is all about, confidence interval. So the word confidence plays a role here because it's used in a similar way to how we would define confidence. When we say we're confident about something, we feel good about what we've done, right? We feel confident that it's correct. And we're going to use confidence in the same way, except we're going to assign a numerical value to it. Numerical value. So we have to talk about what we mean by confidence. And one of the things I will do, because I use this, there's a particular software package that's out in the internet for free, which you are obviously welcome to use too. But I'm going to show you tonight in a demonstration of why this method that we're going to learn tonight works. So the first thing we want to do is we're going to estimate a population mean where, and it says here, the population standard deviation sigma is known. Now, realistically, that's not usually the case. If you don't know the population mean, you probably don't know the population standard deviation. Although some people might argue in a particular field of study that the population standard deviation is more easily estimated than the population mean. So that's fine. But in most cases, this is not going to be practical, but we're going to go over it anyway, just in case you do have an estimate of the population standard deviation. So what do we need? We need the mean, we need a standard deviation, and then we have to come up with something that defines this idea of confidence. How confident are we that the interval represents an estimate of the population parameter, either a mean or a proportion? So those three things we're going to use to create what's called a confidence interval, an interval estimate. So in a nutshell, this book just dives right in and gives you your formula. All right. So let me review the formula for you. To create a confidence interval, we're going to take our point estimate. In this case here, let's look strictly at a population mean. We're going to take the point estimate, the sample mean, and we're going to add and subtract. Now this symbol here where it has the plus and the minus sign below it means add and subtract. So whatever's to the right here, we're going to, first of all, subtract that from the population, that's the sample mean, to get the left-hand part of the estimate, the left endpoint. And then we're going to add the same thing to the sample mean to get the right end of the estimate. Can you picture that? We're adding and subtracting the same value to create endpoints of an interval. All right. So this here, this whole thing that we're looking at here is called the margin of error. And you might have heard that term if you were actually paying attention to the selection and the polling that was being done. There was daily polls that you could look at, and people would say, how about that margin of error, right? You know, here's my estimate. What's the margin of error? Because what the margin of error does is gives you that interval estimate. Okay. So the margin of error is this entire term here in the case of the estimation of the population mean, and we're assuming that the population standard deviation is known. Why is that important? Because if you look at the formula, this right-hand term here, it has sigma in it. You see the sigma there? The sigma is the population standard deviation. So to use this, this formula here, we need to know what sigma is. We have to have a good estimate of it. Now, let me break this into two pieces here. All right, the Z is a Z-score. All right, it's based off the standard normal distribution, okay, with a mean of 0, standard deviation of 1. So the Z is a value plus, it could be positive, could be negative, but in this particular case, we will always use a positive value for Z. To be honest with you, it doesn't really matter because it says plus or minus. So if this is plus or minus, it doesn't matter because it's going to be there. One of the answers is going to be minus, one's going to be plus. All right, so the Z is a Z-score. And that Z-score is going to be related to this idea of confidence that we're going to describe to you, right? So we're going to go into that a little bit. This sigma divided by square root of n should look familiar to you from chapter 8. That's the standard error for a sampling distribution of sample means. That's a standard error. And the Z here says it corresponds to the level of confidence. So what we basically are saying is that this margin of error, what I would call margin of error, which many statisticians call margin of error, is the product of two things, right? No matter what formula you use, it's going to be the product of a number that represents how many standard deviations are you away from the mean, and this thing here called the standard error. So in this case, it's Z times the standard error. That product is called the margin of error, okay? And that's what we add and subtract to the mean to create the endpoints, the left endpoint and the right endpoint of this interval that we call the confidence interval. All right, so far, okay, what I'm saying? Not, yes. All right, not confusing. All right, good. Now, here is the assumptions that we need to use this. This is very important. This whole procedure that I'm showing you here resides on two things. Number one, either the underlying population is normally distributed, or we don't know about the underlying population, or we do know it's skewed left or right, or looks weird, and the sample size is at least 30. That's, of course, the central limit theorem. If we have a underlying population that is not normally distributed and the sample size is less than 30, we cannot use this procedure. We have to come up with something else for a confidence interval. And there are other types of confidence intervals. I'm telling you, they do exist. And actually, one of the types that we'll be looking at is called a bootstrap. But it's technically way beyond this course, all right? This is an introductory course. If you're interested in it, this website that I'll take you to does describe it in more detail. All right, so that's the assumptions. Now, the way to represent the Z is this way right here. The Z is represented by what's called alpha divided by 2. Alpha divided by 2, we'll describe what alpha is in a minute. Alpha divided by 2 is the area to the right of that Z value when we draw our standard normal curve. All right, picture plotting it somewhere. You know, remember 0 is the middle, right? A standard normal curve. And we're only going to use the positive Z. So somewhere to the right of 0 will be the Z that we use. The area to the right of that Z is this alpha divided by 2, all right? And we'll define what this alpha is in a minute, but that's what we're talking about, all right? Does that make sense? The Z is plotted on the standard normal curve, and the area to the right of it is alpha over 2, which if we said 0.025, we meant that for a Z of 1.96, the area to the right, the right tail of that value, the area to the right of it is 2.5%. Okay, that makes sense? curve, plot the z, area to the right, 2.5. That's all. Nothing, no biggie there. You know how to do that, right? How do you find that 1.96 if you know the area to the right? Use inverse normal. All right, easy. Now, this is the most famous of the z's, 1.96, because it's going to be used in what's called a 95% confidence interval. All right. Picture 95% being in the middle. Picture drawing a z, a standard normal curve, in the middle 95%, right? The middle 95% of the curve, okay? The z's that represent the endpoints of that are going to be negative 1.96 and positive 1.96. So that's what these confidence levels mean. If z is 1.645, that means the middle area is going to be 90%. If we have a 99% confidence interval, then the two z's are going to be negative 2.58 and positive 2.58. All right. Make sense? Okay. And you know how to find these values. You know how to find them because it's the area to the right. And remember, to find the area to the right, you do 1 minus the area to the left, right? So all these so-called confidence levels have to do with the middle part of the z curve. Now, the question is, why do we call it a confidence level, and why these numbers? Why are we using these numbers like this? I mean, what's the point of doing that? Well, let's assume the following. Let's assume that we had a list of all possible samples, a sampling distribution, right? That's what we mean. We have a list of all possible samples and their corresponding means for a certain sample size, all right? So you have a list of sample means, okay? Now, what if we created one of these confidence intervals for each and every one of those sample means? Let's assume we did a 95% confidence interval, all right? Using the technology that I just showed you, you just calculate what the z is and then plug it into here. We know sigma, we know n, the sample size, and we calculate the margin of error, and we add it and subtract it to the sample mean, all right? So suppose we do all of that. For every possible sample that exists. And let's assume through some sort of sorcery that we know what the population mean is, all right? That which we were trying to estimate. Assume that we know what it is. The definition of this level of confidence is the following. If you're 95% confident, what that means is that when you observe all those confidence intervals for every sample, every single one of them, there will be 95% of them would have the population mean inside that, the boundaries of that confidence interval. 95% of all those confidence intervals would have the actual sample mean inside of them, and 5% would not. And that's just the way it works. It just works that way. There's no way of guaranteeing. You can get close if you want, but here's the problem. Now, so if I want to be 95% confident that my particular sample can, when I create the confidence interval, that particular sample has a confidence interval that contains the population mean, what I'm really saying is I'm hopeful that the one that I chose, that sample that I got, is one of those 95% and not one of those 5%. And the question is, are you willing to live with that? See what I'm saying? Are you willing to live with that idea that 95% of these intervals contain the actual population mean, 5% don't? I don't know if the one I have is one of the 95% or one of the 5%, but I'm willing to live with at 95%. Now, I did that 95% of them do contain it, And that's what I mean by 95% confident. I'm 95% confident that the one interval I have actually contains the population mean. It's in there somewhere. Now, what if I want to be more confident? What if I want to be 99% confident, right? Sounds better. Here's the deal. Here's the problem. Z is bigger. And if Z gets bigger, what happens? If Z is bigger, this whole term here, assuming the sample size remains the same, this whole term here gets bigger. Which means when you subtract it, you get a smaller left endpoint, and when you add it, you get a bigger right endpoint. In other words, the interval becomes wider. And we don't want that. We don't want wider intervals because that means what? A worse estimate. We want the intervals be narrow, not wide. So most people choose 95%. Now 90% has a smaller z, which means the intervals become narrower, which is good, but we're only 90% confident. It means 90% of all the samples that exist contain the population parameter and 10% don't. That's a worse situation. So you see there's competing, this is not a perfect world here. There's two things that are competing, right? The more confident we become, the wider the interval, which is no good. The more confident we become, excuse me, yes, and if we want a narrower interval, which is good, we have to accept less confidence. So what did statisticians do? I mean, what do researchers do? They simultaneously, if they want a bigger, a more narrow confidence interval, but they want a higher level of confidence, they increase the sample size. Because if Z gets bigger with more confidence, right? To make this whole term relative, to offset that, you increase the sample size. Because the denominator, if you increase the denominator, this term becomes smaller. So if you want to increase Z, you may want to decrease this term to offset it. Sounds good if you have the money and the resources. All right. If you're the US government, you can sample everybody if you want to, right? That's what the US Census does. But if you are a university or you have limited research funds, you're not going to just have as many people as you want in your sample. It's limited, right? There's some limitations of time and money. So I want to bring this out to your attention. Is that what we mean by confidence? Confidence has to do with whether the particular sample that you have when you create the confidence interval for it, whether there's a good chance it contains the population parameter or doesn't. Many students make the mistake of saying the following. This is a mistake, by the way. If you see it on an exam, no, it's a mistake and it's wrong. They will say, there is a 95% probability. This is what they say. Pay attention. This is a 90. I see your attention going elsewhere, which is fine. It happens in my household all the time. I say there's a 95%. If I say there's a 95% chance that the interval I have contains the population parameter, I am absolutely wrong in saying that. That's not what a 95% confidence means. It doesn't mean there's a 95% probability. Either it contains it or it doesn't contain it. Okay? Once you've chosen your sample, it either contains, when you create your confidence interval, either contains it or it doesn't contain it. All right? We cannot say there's a 95% chance. No, there's not a 95% chance. It's a 50% chance of it having it or doesn't have it. There's no 95%. The 95% is the level of confidence that we have that it contains it. All right. It's not the same thing. It's not a probability. Now, the way we treat the confidence level, when we calculate the Z, we treat it as if it's a probability. Why? Because we're dealing with samples. We're dealing with samples. And what we're doing is we're choosing one of the samples out of the sampling distribution. That's different. That's different. It's not a probability that we're calculating. This Z here represents a probability. Okay. But it's the probability of what? It's the probability of being 95% confident. It's a very subtle thing here. All right. It's the probability of being 95% confident. It's not the probability of choosing of that particular sample that's being chosen, of having, it's not the probability that that sample, when we create the confidence interval, will contain the population value. No, it's not that. It's based off confidence level. All right, confidence level. How confident are we? So we use the sampling distribution and what we do here is the following. What if we want to find Z and we want to be 95% confident? Remember, it's an interval, right? Interval that we're coming up with. So to find the 95% confidence interval, the middle 95%, the interval is going to be wrapped around what? It's going to be wrapped around Z is equal to 0. All right. What's left from 95%? 5% is left for the rest of the curve, but the curve is symmetric. So half of it's to the left and half of it's to the right. 2.5% left, 2.5% right. Does that make sense? And that 2.5% to the right of the Z that we want means there's 97.5 to the left. A very common mistake. This is why students don't do well in statistics. A very common mistake is they see 95% interval and they say, oh, I just need to find the area to the left is 95%. No. Remember, 95% is just the area in the middle. How about that left tail? Left tail is 2.5%. 95 plus 2.5 is 97.5. That's the area to the left. That's what you put in to your normal distribution to find this Z, 1.96. And the only thing you're doing is finding the Z. So you're putting in a mean of 0, standard deviation of 1. That's all you're doing. You're finding the Z. How about a 90% confidence interval? Why don't you tell me what area to the left of this Z of 1.645, what area to the left would you put into your calculator to find it? If the area in the middle is 90%, what's the area to the left of the Z?
95%.
95%, that's right. Because 10% is left after you have the 90% in the middle, 5% on the left, 5% on the right. The middle 90 plus the left tail of 5 gives you 95%. How about this 99%? What's the area to the left?
99.5%.
99.5%. So I want to make sure that you understand that. That's really important. All right, because you're going to be using Excel probably, or we'll use Minitab too. I guess I guess Minitab might be easier in some ways to come up with these Z's. All right, but you can use Excel, and that's what you would use for that area to the left. They call it the cumulative area, right? The area to the left of the Z. So that's where they come up with these Z's. That's where they get the Z's from. Remember, it's the positive Z's. The right endpoint is what they're using. And so when you get the Z, you plug it into here. You're going to be given sigma. You're going to be given n. and you just calculate the margin of error and add and subtract it from the sample mean. That's it. Now, the sample mean either is going to be given to you or you'll have a data set and you calculate it. But you know how to figure out sample mean, right? It's easy, right? You're given some data. You can do it in Minitab, you can do it in Excel. You just look up the sample mean and there it is. Just be careful that don't use, if sigma is given, this is the formula that's preferred. Do not use the sample standard deviation that's given for the data set. There will be a time where you will use it, but if we do know sigma in the problem, we use it. This formula is more accurate than the one that we'll see in a few minutes. So you need to, if sigma, the population standard deviation, is given in the problem, we do not use the sample standard deviation as a replacement for sigma. All right? And that's it. That's all there. I mean, confidence intervals are actually pretty easy to do because there's a formula. You just plug in the numbers and you're done. That's it. There's nothing complicated about them. The interpretation is more complicated because let's look at an example here. Let me see if they have an example. Here's an example here. It says, from past experience, the population standard deviation of rod diameters produced by a machine has been found to be 0.053 inches. For a simple random sample of 30 of these rods, the average diameter is 1.4 inches. All right, there's your sample mean. What is the 95% confidence interval for estimating? They should say for estimating population mean. Now, by the way, if a problem in the future says something like, what is the estimate for the population mean? And the answers are all confidence intervals. Don't be upset. Don't think there was a mistake. That's the interval estimate. If we have a list of individual values, those are the sample means. And they want a point estimate for that answer to that question. All right. So if you see one number, it's a point estimate. If you see in intervals, those are the confidence interval estimates. Okay. But they both of them are estimating the population mean. It's just the interval estimates are better because what does it do? It takes into account sampling variability. All right. You see why? You don't want to use your sample mean and say, that's it, I'm done. Here's my estimate, I'm done. Because Steve, you may come, in this case here, you come up with 1.4, and Han, you come up with 1.6 inches from yours. And then you look at each other and say, no, you're wrong, I'm right. All right. What kind of life is that? It sounds like the political drama we're going through right now, right? You're wrong, we're right. Well, you're both wrong because the population mean is probably somewhere in between. So it's better to have an interval of estimates and say, I'm such and such confident that the actual population means inside that interval. That's better than saying, I think my point estimate's better than yours. So forget about that. All right. No, that's not good. Now, what is the standard error? Now, here's the deal. If I ask for the standard error, I'm asking for sigma divided by the square root of n. Make sure you understand the difference between standard error and margin of error. All right, students get confused with that. The standard error is this. It is the standard deviation of the sampling distribution. That's a standard error. In this case, sigma divided by the square root of n. Well, sigma is 0.053. Square root of the sample size, we have 30 rods. So this number here is the standard error. We multiply this by what? Well, if we want a 95% confidence interval, we know the z, we've already discovered this, right? The z is 1.96. So 1.96 times this number gives us our margin of error. All right. And that's what we add and subtract to 1.4 to get our confidence interval. That's what they do down here. 1.96 times the standard error. Add and subtract that from 1.4, and you get this here. Now here, I want to ask you a practical question. How far apart are these two numbers? I don't want you to subtract them. I want you to give me an answer in words that does not involve numbers. How far apart are these two numbers? I don't want any numerical response. I want you to tell me how far apart are these two numbers based on the definitions I've said so far. Standard error, margin of error, Z's, all that sort of thing.
What's the question again? They're how far apart are they, or?
Oh, yeah, but I don't want a numerical answer.
Okay.
Well, I do want a word that has a numeric number associated with it, but I don't want you to say, all right, I'm going to subtract those two numbers and here's my answer. No, I don't want you to do that. I want you to say it in such a way that it uses one of those phrases I just said. Z, standard error, margin of error. I want to see that if you understand the mathematics of what we just did, because it's very important to understand this in terms of what your answer is going to be.
I don't think this is the best way to say it, but I would say that the numbers are separated by double the amount of the Z-score corresponding to 95% confidence.
You're saying
scale.
too much. You're saying too much. The double sounds good. Double what? 3 words.
Double Z times.
No. 3 words. Words. It's double the, and then 3 words. One of the words has a 2-letter word that's typically used in sentences. I don't mean to make your life miserable, but it's double the margin of error. Isn't it? Why is it double the margin of error? Because we're adding and subtracting the margin of error from the same value. So the distance from the left endpoint to the mean is the margin of error, and the distance from the mean to the upper endpoint is the margin of error. So therefore, the distance between the endpoints is twice the margin of error. So if I give you a confidence interval and I ask you what the margin of error is, and I don't give you anything else, other information, Steve or Han, I don't give you anything else. I'm not giving you the confidence level. I'm not giving you the standard error. I'm giving you zilch. I'm just showing you, I'm displaying to you a confidence interval, and I'm saying, what's the margin of error? Just subtract the 2 numbers and divide by 2. That's all. It's double the margin of error. Why is that important? Because if you were going to explain what the mechanics of what you're doing here, what if you, is it Steve? If you're going to explain this to your wife, you have a wife? I don't know if maybe you're single. I don't know. I don't care. Han, I don't care if you're married or not. Whoever is the person that you commonly talk to, whoever that person may be, maybe you have a dog. Whoever you're telling it to, hopefully a human being, the point I'm making is they don't know Z's and standard errors, but they've heard the term margin of error because they've heard it on the news. And you say, all right, it's double, the confidence interval is twice the size of the margin of error. And they said, oh, I heard about margin of error. I don't know what it is, but I've heard the term. But that's exactly why you want to know it. Because you want to know how you constructed that confidence interval. Now, the actual mechanics of these things that we're multiplying, dividing, these are particular mechanics that I am showing you because that's the typical way of doing it. But there are other confidence intervals that use the same idea of adding, subtracting a margin of error. Okay? So if the confidence interval is symmetric, and it doesn't have to be, by the way, but we're assuming symmetric around the point estimate, then we're talking about twice the margin of error is the distance between the endpoints. Okay, so the margin of error is giving us what? A methodology for describing variability from sample to sample. All right, it's giving us a methodology of creating variability around our point estimate. Why is that important? Because without the margin of error, there's no interval. So don't get bogged down with the idea, and I'm glad you did this, Steve, because I think most people would have done it exactly the way you said. Well, it's twice the z times the sigma, blah, 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 blah. You know, whatever you want to say. That's exactly right what you said. But if you said that to some person off the street, they're going to look at you like, that's the last question I'm ever going to ask you. What are you trying to show off? But if you say twice the margin of error, they'll say, it sort of rings a bell because they heard the term somewhere. And people do say it on the news. I heard it on CNN the other day before the election. Somebody was saying, you know, here's the estimate and here's the margin of error. And the person was saying, yeah, that darn margin of error. I've heard about that. What the heck is, you know, they talked as if they knew what it was. And if you explain it to them, that you say, all right, you take that number and you subtract it and take that number and add it, and then you get this range of values. People would understand that, I think. They would understand it. So that was why I asked that question. I asked it not because I'm being a smart ass, excuse me, smart, well, whatever. But I was saying it really have you understand what exactly this whole process is. And here is a margin of error right here. Here's here, you know, you draw your normal curve. Now this is a standard normal curve with a mean of 0. And your left endpoint, if it's 95% in the middle, the left endpoint's negative 1.96 and the right endpoint's 1.96. And again, the way to find this is to use the cumulative area. So the area to the left of this positive 1.96 is this 95%, plus this area to the left here, which is 0.025 or 2.5%. And that's what you would put into your calculators, 0.975, 97.5% to the left. Okay. So going back, when they write the z, they write it as what? Z with, and then in the, here, go back to the alpha divided by 2. Where are we? This thing. The symbol alpha divided by 2. Alpha is what? For 95% confidence interval, it's 0.05. It's what's left over after you do the confidence interval. So the confidence using the symbols is 1 minus alpha. 1 minus alpha is the confidence level. All right. This is the way, this seems very strange the way they've done it this way, right? It makes, you know, you'll see why, and maybe in the future when we study hypothesis tests, why they talk about it in this way. But the alpha is the amount of the area under the curve that remains after you subtract out the confidence level. All right. So 1 minus alpha. So alpha in this case would be 0.05 if the confidence level is 95%. All right. So 1 minus alpha, 1 minus 0.05 or 0.95 is the confidence level. So I just wanted to bring that to your attention because people get confused with that also. It's unfortunate, right? The symbols confuse people when this concept is pretty easy, I think, to understand what, you know, in general what we're doing. And I've taught this to many students who tell me they've never understood anything in math ever, and they understand this. All right. So it's not that it's a hard concept, it's just the symbols are so opaque, I think. You know, they're just really hard to understand what they mean. All right. So, you know, this is an example here. For, you know, if you know 1.4 is the point estimate. And then we subtract z times the standard error. We subtract that. We get 1.381. It has to be, if we subtract the margin of error, it has to be that the difference between these two numbers is the margin of error, right? It has to be that if we're subtracting it. We're subtracting the margin of error. That means the distance is the margin of error. That's what subtraction means. If we add the margin of error to get this number, that means this distance is the margin of error. What is the margin of error? You can tell it's 0.019, right? When you subtract these two numbers, 0.019. Therefore, the distance between the endpoints has to be 0.038. It's 2 times 0.019. 0.019 plus 0.019 is 0.038. Okay, so this is a very nice, to be honest with you, I don't see this in many books. It's a very nice pictorial representation of how a confidence interval is created. I like it. It's beautiful, actually. I can call statistics beautiful. It's a beautiful representation. So in your book, this is, highlighted, because this is something that really tells you how to do it without giving, step-by-step instructions. It really tells you what to do. Very nice. Okay. Now, here's the interpretation. If I ask you to interpret it, this is what you should interpret. You do not say there's a 95% chance that the actual mean is between these 2 points. That's not true. Because this is just one interval. You had a different sample, you would have a different interval. When I say list all the different samples for the sampling distribution and create a 95% confidence interval for each one of those, they're all going to be different. They're all going to be different. Why? Why are they all going to be different? Because the mean is different for each one. Basically, the margin of error is going to be the same, isn't it? The margin of error will be the same for each one of those samples if we know sigma. But sigma is going to be the same for all of them, n is going to be the same for all of them, and z is going to be the same for all of them. That means the margin of error is the same for all of them. All of them are going to have 0.019 as the margin of error. The difference between them will be x bar. Isn't this a beautiful methodology? The methodology is not dependent on what? The construction process. Excuse me, the variability of the confidence intervals is not based on the construction process. The variability is based off of the point estimate being variable. But instead of just using the point estimate, we're creating an interval around the point estimates. All right, so some of them are going to be to the left, some of them are going to be to the right, some of them are going to be in the middle. You see what I'm saying? They're shifting around. All right, let me show you the software. I'll stop for a second. I'm going to actually, I wasn't planning on doing this, but I thought of it when I signed on tonight. I'll show you how to get onto this. All right, so let me go back. Just signed on here. Now, this is something you can play with as much as you want. It's free. It's a free website. So where are we? Here it is. It just, if you don't remember, you could just remember that it's called StatKey. And you can simply just in your browser, you can search for StatKey, and the first thing that pops, actually, let's just do that. I'm just going to type in StatKey. And what pops up in my browser, the first thing says StatKey Lock 5. This software was created with help from people from Stanford University and some other places, some software engineers there. It was created by these 5 people: Lock, 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 and Lock. I know, Han, you're enjoying this tonight. Who's Lock? Is it just somebody who just loves the word lock and they just repeat it 5 times? They like their last name so much. No, this is a family of Locks.
Oh, really? Okay.
And they're all statisticians. Husband and wife, married, both professors of statistics, and then they have children. They all became professors of statistics. Weird, right? There's a whole family of statistics professors, and they all created this textbook, which uses what's called simulation to show you some of these concepts, makes them easier to understand. So let me show to you. Now, I will show you actually when we get to doing the mathematics with confidence intervals. We'll go to the software and actually create a simulated confidence interval. This is a different method of creating a confidence interval called Bootstrap confidence intervals. And I'll show you how to create one, and then you'll compare it to the calculations that you're doing, and you'll see it's pretty similar actually. But here's part of this website here. It talks about sampling distribution. So let's look at a sampling distribution for mean. I'm gonna click that. And hopefully it'll open up. There we go. Now, they have a bunch of data sets here on the website for these sort of demonstrations. So I'm going to pick one of these, statistics grad schools. So some variable that's being measured. Suppose we have 82 grad schools around the country, and we're asking each grad school, how many graduate students do you have? All right, for these 82, how many graduate students do you have? So as you can see, each of these dots represents the number of students for that particular grad school. So there is a school has 196 students in their graduate department. Maybe it's graduate department of statistics. I'm not sure. Here's one that has 163, 145. So you get the idea. This is a dot plot, right? Of those numbers of students, and there's 82 dots here represented. Now this is a population, and suppose we wanted to take samples of size. Let's make it. Well, it says 10 here. N is equal to 10. That's a sample size. Let's make it 15. Right. I want to create samples of size 15 out of this population of 82. All right. I'm creating samples of size 15. And it uses, what does it do? It uses simulation to do this. Simulation means it's telling the computer, create one of the samples out of the sampling distribution. Create one of them. All right. So I'm going to click generate one sample. Here's a sample that has 15 of these 82 and has a mean of 51. So here are the 15 that were chosen out of the 82, randomly chosen. All right, that 163 one is still there. All right, the one that was 196 is not in the sample. All right, the one that was 145 is not in that sample. There's one that's 117 that's in the sample. All right, you get the idea? Random sample of 15 out. All right, and the mean is 51. And notice that just in this main area here, it shows that dot. Suppose I want to create 2, 3. Notice that the samples are changing here because it gives you the very last sample that was chosen, what its mean is. All right, 43.8. All right, so we keep going. Let's just create, how many have we had so far? 5, 6. All right, let's create 10. All right, I've created 10 samples. And here's a dot plot of what? Of the sample means for how many samples of size 15? 10 samples. This is like a mini sampling distribution. It's not all of them, right? It's just some of them. What if I wanted to create another 100? What if I want to create another 1,000 of them? About another 1,000. Doesn't that look like a normal curve? Look at the original curve. How would you describe the original population?
Positively skewed.
Positively skewed. And yet look at the distribution here of Now, if we reset, let's just reset and let's just choose 10, 20, 30. Doesn't look normal yet, right? But if I choose 100, it starts looking normal, and 1,000, another 1,000. You see, it looks more and more normal, all right? So you get the idea? All right. Now, N is 15 here. And yet we eventually got to what? We got to a sampling distribution that looks normal. Remember, if the population is skewed, you need at least 30 in the sample size for us to assume, right? In other words, 30 had to be in here for N for us to assume the sampling distribution is normal, but eventually it does look normal anyway. If we choose enough of these samples, all right? We choose enough of them, we'll start to see some normality. Okay, this is a representation of a sampling distribution that's incomplete because there's got to be zillions of these samples, all right? Many, many, many samples. And actually there's 82 choose 15. That should be the number of samples. 82 choose 15. You put it into your calculator, you're going to get a pretty, I don't even know if the calculator is going to give you the answer, but let me try it in my calculator. 82, and I'm just using the TI 84. Oops, wrong thing. And 15. Yeah, it's 10 to the 15th power. All right, that's how many samples, almost 10 to the 15th power. That's our little, how long the list is of the number of samples and sampling distribution. I'm not going to be able to do this with this software, all right? It's not going to work. So, but this is a simulation. I generated how many samples? 2,130 samples. What if I wanted to find a confidence interval using this method here? I just click the two tail here, and this is a 95%. And notice that the answer runs from 37.45 all the way up to, I have to move this out of the way because my pictures are there. So 71.2, 71.25, 37.45, 71.25 is our confidence at 95% confidence interval, right? What do these black dots represent? These black dots represent the 95% of the 2,130 what? 2,130 samples. Yeah, 95% of them are all these black dots. And these red dots here, the ones to the right are 2.5% of the 2,130, whatever that number is. That's the number of dots here. And 2.5% of the 2,130s to the left. Pretty cool software, right? That it does this. It's a simulation. But here's the really cool part. There's a button here called confidence intervals. So I click that. It's actually, let's just reset. Let's do another one of these. Assuming, what are we going to assume here for this population? Let's go back. The population mean is 53.537. Okay. We know what the population mean is. We don't know that typically when we're estimating the population mean. We don't know it, but in this case, we know it. Suppose we select one of these samples. And here's the sample, has a mean of 70.267. Here is a confidence interval that's created around that sample mean. You see how it crosses in the middle bar here? This middle bar here is U. That's that number we saw before. What was that number? 53.537. That's what this line here represents. Okay, get the idea? So if I create another one, create another one. Oh, look at the red one. What's the red one represent? Notice that the mean of 53.537, the population mean, is not inside this interval. All right, you get the idea? It's not inside that interval. All right, let's generate another one. Another one. Another one. Another one. How many have we done so far? 6, 7, 8, 9. So the first 10, 1 out of the first 10, okay, doesn't contain. So 90% of these intervals contain the true population mean, and 10% doesn't, that 1 out of the 10. And if I keep going, let's go to the 20, see if we get any more of these reds. Oh, that's pretty interesting. We only got 1 out of 20, but that's 5%, isn't it? Doesn't always have to be so exact, right? That's 1 out of 20 of these sample, of these what? Confidence intervals. These dots represent what? The sample means. See? Sample means. This sample mean is pretty close to the real sample mean, isn't it?
Mhm.
Yeah. Only 1 out of 20 is not. Now, if we did another 10, another 10, another 10, another 10, we should get some more reds, but I'm not seeing any. I only got 1. This is unusual. We should see some more, but remember, this is simulation. Let's choose another 100. Oh, there's some more. Here's another one here. There's 2 out of 190. We're going to get more reds. There's more. There's 4 now out of 290. There's more. 1, 2, 3, 4, 5, 6 now out of 390. Get the idea?
Mhm.
This is just simulation, creating these reds. How many now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 now. Intervals out of 590 that don't contain, which means the remaining do contain the population mean. All this green are intervals that contain the population mean. All right? This is what we mean by confidence. Out of the 500, in this case, out of the 590 intervals that I've created through simulation, sample intervals, right, which exist. And what did I say? There were 15? Okay, 15. That means there's 575 of these intervals that do contain the population mean and 15 that don't. So if I was going to be exact about this, I would say my confidence in this is 575 divided by 590. So I'm 97.4% confident so far. But if I could list every single sample that exists, remember how many I told you, 10 to the 15th, right? Or 10 to the 16th, whatever that number was. Yes, I think it's 10 to the 16th of the number of these intervals that I could list. There should be almost exactly, if not exactly, 95% of them that do contain the population mean and 5% that don't. All right, because when you create the intervals, they just don't contain the population mean. So this simulation shows you that what we end up with, exactly what we end up with, is pretty close to what's predicted. Oh, and by the way, here we go. It says it right here. I was wrong. It's 14 out of 590. This is called, by the way, and this is more advanced, but both of you are advanced students, so I'll tell you anyway. This is called coverage. In other words, there's a predicted amount that you would predict with a 95% confidence interval. You would predict 95% of the intervals which would contain the interval, given a 590 samples, a small number of samples compared to the actual number of samples that are out there, we get even larger coverage. We get 97.6% coverage. That means for these 590 samples, only 2.4% of those samples out of the 590 that are listed here, only 2.4% of them do not contain the population mean. Right? You like to simulate? It's great, isn't it? It's fantastic. It's a great way of displaying to a student how this works. That's what we mean by confidence. All right? Now, it's possible that one of these intervals that you should, you choose one of these intervals. Most of them are green. You're hoping it's one of the green ones. Could be one of the red ones. But there's not many red ones out of these 590, are there? It's only 14 of them. Okay? 576 of these 590 intervals have the true mean inside the interval. That's all these green ones. Look at it. You can't even see the green ones anymore. They're all smushed together. You can see the red ones because there's only 14 of them. And this is the logic behind using confidence intervals. This is what I mean by confidence. It's not a probability. It's basically saying, I'm 95% confident. Well, in this case, I'm even more confident. In this case, we could say I'm at least 95% confident. All right. That the interval I chose out of all these intervals actually has the true population mean inside that interval. And the construction of that interval, like the construction of all of these intervals, is that methodology that I showed you before. It's Z. We create a margin of error, which is Z times sigma divided by the square root of n. That's the construction process. All right. Now, by the way, you can hit this two-tail thing here, and it gives you your confidence interval. Now, this is an estimated confidence interval. Why? Because it won't match the confidence interval based on your interval. It won't. It's based on 590 intervals here. You're creating a confidence interval, 95% confidence interval. How does it do this? It simply counts. All right. 95% of the dots in the middle are part of the interval. And the 5% that are outside that interval are the red ones here. Right? So that you just count the number of red ones, subtract them from 590, and that's the number that's in the middle. Okay? And that's why they come up with these endpoints here. Notice the endpoints are right where the red dots begin here and where they begin here. All right? Simulation. So if we don't use the construction process that you use for this particular, now let's go back to the original sample here. Here's your population. Let's just choose one of these samples. Actually, we already chose one, but let's choose, I'm going to choose one of these near the middle here. I'm going to choose this one right here. This is what's beautiful about the software. If you just put your cursor over one of these dots, it shows you the sample right over here. Right? And if you just move it around, notice it just, your eyes kind of go buggy when you do that. But, I'll choose that one. What's the mean for the one I just chose? Oops. Sorry. There it is. The mean is 56.467. Now, what is the population standard deviation? 36.89 is the population standard deviation. The sample standard deviation is 51.2. We don't use that. Population standard deviation is right up here, 36.89. So if I was going to create a real confidence interval based on that particular mean, all right, We know the sample size is 15, right?
Mhm.
So the sample size is 15. So sigma is 36.89 divided by the square root of 15. I get 9.52 as my standard error. Multiply that by 1.96 because it's a 95% confidence interval. I get 18.67. Let's use 18.669 because we have 3 decimal places here. So 18.669. All right, we're going to add that to our sample mean, which is 56.467. And then we're going to take 56.467, the sample mean, and subtract 18.669. And I get a confidence interval of 37.798 on the low end, 75.136 on the upper end. It's not exactly what you see here, but the low end number is pretty close. The upper end number is a little bit off. But I'll tell you the reason. The reason is because if you remember, the standard error only works when the sample size is 5% or less of the population size. And 15 divided by 82 is 18%. If I had much bigger population, right? If I had a population maybe 1,000, then this interval here would be very close, pretty close to the interval for any one of these samples, any one of the samples, pretty close. But this is a way of doing it, of coming up with a confidence interval. Now, but it's not great. It's not great. So I want to show you one other thing. Let's go back to the original main screen. In here, this is the proper way to simulate confidence intervals not using the formula. It's called Bootstrap. So I'm going to click this one here. And again, we have data sets. I'm going to pick one of these data sets. Let's pick the Mustang price data set. Now, what's realistic about this way of doing it is that we don't know the population at all. These data sets are all samples, all samples. There's no population information. So what is the, so we have an original sample. Let's see how we're doing time. All right. We have the original sample, 15.98 is the mean, and the sample standard deviation is 11.114. Okay. Suppose we wanted to create a confidence interval in a different way. I'm just showing you this different way. Now, remember, I talked about sampling with replacement, sampling without replacement. Remember I talked about that at one time? What this is really cool. What they do here is they take the sample that you have, whatever it may be, and what they do is they do sampling with replacement from that sample, which means you can take that sample and literally choose the same thing more than once if that's the way it works out. All right. So it's going to take a sample of 25, but there could be repetitions of the same item coming out. So you create one of these bootstrap samples. So notice here that there's in this sample there's a 45, which by the way represents I think the price of a Mustang, 45,000. All right, I guess a used Mustang. Doesn't show up on this sample. Okay, this one here, 37.9, which means $37,900, shows up here. Notice that 3 of these show up at 32,000. There's a couple 32,000. There's a 32,000, a 32,500. So it is choosing some of these more than once and not choosing others. All right, because it's sampling with replacement. Suppose now, let's just reset this. Suppose we choose 1,000 of these samples, these bootstrap samples, taking the same sample and just doing sampling with replacement, and just finding 1,000 of these things. Look what we end up with. We end up with, each one of these are bootstrap samples of size 25. Okay. The original sample had a mean of 15.98, but there is one sample here that has a mean of what? 22.964. It actually chose, that particular bootstrap sample chose this one here, this $45,000 Mustang. It chose it several times. Okay. Again, simulation, it can do that. And there's one down here that shows many of the smaller ones, the smaller prices, and not so many of the larger prices. All right. So again, these are called bootstrap samples. Now, what if we did a confidence interval for this one? I'm going to do the two-tail again. Here's my 95% confidence interval. And it says it's from 12.292 to 20.504. Now, we're going to assume here, because the sample size is 25, we're going to assume what? We're going to assume the population's normal, all right? In this case here, we have to, right? Okay. But with bootstraps, we don't have to assume normality, but we will if we wanted to calculate our confidence interval. Now, if we wanted to do a 95% confidence interval, let's just make an assumption here. Let's assume that the population standard deviation is 11. All right, I'm just going to make that assumption. All right, there's no information here about that. I will, when we actually get to the point where we don't know the population standard deviation, I'll show you how to calculate with a formula, how to calculate confidence intervals. We'll do that next time. But let's assume population standard deviation is 11. All right. Let's calculate the margin of error. So if the population standard deviation is 11 and the sample size is 25, the standard error is 11 divided by 5, which is 2.2. We multiply that by 1.96, which is the Z for 95% confidence interval, we get 4.312. So I'm going to take my mean, which is 15.98, and I'm going to subtract 4.31. And I got 11.67. And I'm going to take my 15.98 and add 4.31, and I got 20.29. Not that bad. Not bad. I got 11.67 on the left endpoint, and I get 20.29 on the upper endpoint. And it's the interval that comes up with this bootstrapping is pretty close. Better than using the sampling distribution that we did before. This is a better method. So this is an alternative to what if we did not have a population standard deviation. We could use something like this to come up with an estimate of the confidence interval for that one sample by using these so-called bootstrap samples. Notice that the mean of the bootstrap samples, I picked how many of them? 1,000 of them, is practically 16, right? It's 15.999. It's very close to the mean of the original sample. So this is an alternative to doing the calculation through formulas, where we don't have to worry about normality of the population. Do it this way. It works pretty well. It's a reasonable estimate. It's being done through simulation as opposed to, real numbers. And if I wanted to add more samples, there's 2,000 samples. By the way, I could change the middle to 0.95 again. Now it's between 12.052 and 20.468. To be honest with you, it didn't make much of a difference, did it? Didn't make too much of a difference. It was practically the same numbers as before, just changed a little bit. So this is a reasonable confidence interval for the original sample, this particular sample. All right. Previous page, the previous thing that I was demonstrating to you was what a confidence level means. Here, we're going to say, all right, let's create a confidence interval through simulation, as opposed to using formulas. And this is one way of doing it called bootstrapping, okay? Using the original sample. All right. One other thing I want to look at in the book, just hold on 1 second. Go back to the book. So this is the methodology that we're using in the book. We're not using bootstrapping. We're not using any other method. We're using the sampling distribution to come up with these intervals, using the idea of confidence. And I showed you through that software program, showing you, we counted the number of intervals that did not have the population parameter in it, and it wasn't very many, right? It was pretty good. So that's, we're counting on that, not the bootstrap. We're counting on that to do this methodology. This methodology depends on this idea that ultimately 5% of all intervals will not have the population parameter inside of it, and 95% will. Okay, that's what we're counting on. All right, and that will work not only for means, but also for proportions. And let me just show you the proportion one real quick. Oops. Let me just go back. I have to go back and re-sign in. Just give me a second. And re-sign in. This is what I don't like about Cengage, is they sign you off too quickly. It's very annoying. All right, just a couple more things. I know it's almost time to stop, but I hope this was helpful tonight to understand this. What I'm going to do next time, I'm going to show you the formula used for estimating a mean when the sigma is unknown, but I'm not going to do that yet. I want to show you the one for population proportion. Now remember, the standard error was for population proportion. The standard error is the square root thing, right? If you remember, it was pi times 1 minus pi divided by n, the square root of all that, right? Look what they're using here. We're estimating the population proportion pi. We don't know what it is. So what do we put in that standard error formula? We have to put in, when we don't know pi, we have to put in p, the sample proportion. That's what we come up with our sample, right? Our sample is going to give us a sample proportion. And that's what we plug into the standard error formula. Instead of pi, we put in the p. So so z, it's the same z as we talked about before, times the standard error. And the standard error for a proportion is going to be the square root, standard error, using p instead of pi. So z times this is the margin of error. Margin of error is z times the standard error. The standard error for a confidence interval is the square root of p times 1 minus p divided by n. That's the difference between the two. If we're going to be given a sample proportion, or we have to calculate it, right? They might give us the sample size, and then they say the number of successes, right? So you just divide those two to get our sample proportion, right? N is our sample size. Z is, of course, what we calculated, what we know. We find Z exactly the same way as we did before. So here's an example. It says in a April 2000, boy, these are really old, 2007 poll, 1,008 adults were randomly sampled from across the US. In response to the question, all in all, do you think that things in the nation are generally headed in the right direction, or do you feel that things are off on the wrong track? 22% responded headed in the right direction. So 0.22 is our sample proportion. They could have just given us the number of people, right? They could have just simply given us, let's see, what is 1,008 times 0.22? Well, actually, fraction, but number of, but anyway, assume that 0.22 is the calculated sample proportion. So actually, it's very easy to calculate the margin of error here. We don't even need to know any standard deviation here, right? No standard deviations to be considered for proportions. We always use the Z, and we just plug in the P here, and you plug in the P here and here, and the N here, and you're done. It's easy. Just plug in the numbers, you get your answer. So proportions are really easy to create confidence intervals. We just simply plug in the sample proportion here, here, and here, plug in the Z here, the sample size here, and we get our margin of error, and we add and subtract it to the P here. All right, so in this case, the answer is going to be 0.22 plus or minus 1.96 times the square root of 0.22 times 1 minus 0.22, which is 0.78, divided by 1,008. That's the number of people in the sample, right? And then 0.2222. So it looks like the margin of error, by the way, is 0.026, right? 0.22, if you subtract 0.246 plus minus 0.22, you get 0.026, right? 26. So margin of error is 0.02. And you add and subtract it from 0.22, you get these two numbers here. And that's our, so we're 95% confident. That's how we say this. We're 95% confident that the true population proportion is between these two numbers. That's how we say it. We don't say there's a 95% chance the true population portion is between the two numbers. That's incorrect. We would say we're 95% confident that the population proportion is somewhere in between these two numbers for this particular sample. We're 95%. We're hoping that this sample here is one of the 95% of them that contain the true population proportion. That's what we're saying. Okay. So that's it for tonight. That's all I want to do tonight. And next time, on Thursday, we're going to look at how to calculate we're going to go back to means, estimating population means. We're going to learn how to calculate a confidence interval when we don't know sigma. And we're going to learn something brand new continuous probability distribution. And it's called the T distribution. We're going to learn about that next time. So that's why I'm doing that as a separate lesson. And then next time, in addition to that, we're going to learn how to figure out sample sizes. Because as a researcher, this is very important. As a researcher, before you actually do any research, before you actually do this, you interview anybody, you have to determine how many people you need to interview. You're just going to pick some number. Han, we're not going to do that. There's a way of calculating the minimum sample size. Using what? The margin of error formula. The margin of error formula is the key to calculating the sample size that we need to conduct research. What do we need? We need two things. We need to know our level of confidence that we want. So actually in real life, we choose that up front. We want to choose our level of confidence. And then, interestingly enough, we want to determine how wide our confidence interval is. We want to make that determination. We want to know, we're going to say, I want an interval that has this width. What's that width? It's twice the margin of error. Get the idea? So I want to determine the margin of error that I want, and I want to determine the level of confidence that I want. And therefore, I'm going to say, all right, how big of a sample do I need? What's the minimum sample size that I need to meet those criteria? And it's not that hard to do, but I'll show you how to do it next time. That'll be the second thing that we're going to learn how to do next time. And that will be it for chapter 9. All right, as far as theoretical. Are we going to spend another time next week doing it? Yes. Next Tuesday, we will do problems. Everything that we covered in chapter 9, we're going to do problem solving. And that'll be it for chapter 9. And that means what? That means you'll have your break. Next Thursday's Thanksgiving, there's no class. Yay, right? No class. No, Han, don't come to class. I won't be here. I won't be able to think anyway. I'll be too much turkey in the belly. It's not going to work. So no turkey in the belly. Anyway, that's it for now. So any questions? Anything that you wanted to go over, or was it good? Was it worth it?
Good.
It was pretty clear. I liked the demonstration. I have one question. Could you repeat so tomorrow at 6 a.m. the test will be up, and we have until when to do the test?
Friday at 11:59. Will that be enough time?
Sure. Yes. Thank you.
Han, will it be enough time? You got
Yeah.
3 full days to pick a time, a 90-minute period of time to sit down and do it. I think that's reasonable.
Yeah. Yeah. I was hoping you'd say Friday. I forgot.
Yeah, it's Friday. It's Friday. And make sure, this is very important, make sure you review before you go in. All right? Make sure you review some. So I would say if you have the time, take
notes.
Fantastic. Fantastic. Take a couple of hours to review. Make sure, because there's sometimes you'll forget things, right? That was covered earlier. So do a review. And go over sample questions, right? The sample questions from each of the chapters that we went over, either in class or in the homework. And make sure you review that before. Let me stop sharing here. Before you actually take the test. All right. So hopefully you have enough time to do that also. All right. Does that sound okay? Okay. All right. So my job now is to go through the test myself. I want to make sure it's okay. And then it'll be ready for you tomorrow morning when you wake up, if you want to dare look at it. No. I don't even have to bother making it available. Well, I don't know about Rose. Maybe Rose has to take it early in the morning, so I have to make it available for her. All right, guys. So I'm going to stop the recording now.